Welcome back to the playing with MPLAB and the Arduino ATtiny85. In this video we're going to look at the fuses. Well, I thought today I'd have a look at the Arduino ATtiny settings on the low fuse byte, which concerns the clock, because if you want to move away from what it does when it arrives to speeding it up to do things faster or slowing it down to save current and power, then this is where we need to start looking. As you can see here, it says some things are programmed and some things are unprogrammed. Now we can see here that bit 7 of the low fuse byte clock divide 8 is programmed, and that's a factory default. That's how an ATtiny would be shipped as a chip. When it's assembled on the board, if they put a bootloader in, then they may change it. If they put a crystal on the outside, they may change it, because this is going to use as default the calibrated internal oscillator. We go through here and we can see that there are some settings. Startup time setting. This is all well and good looking at that, but do you know what it means? So first of all, divide by 8 is quite easy. Whatever clock you pick, it goes through a divider and comes out 8 times slower. Clock out, there's another simple one. If you enable it, then you lose a pin because the clock comes out that pin. Now you only want to do this really if you want to synchronize some external logic to the internal clock of the micro, or you just want to use a clock externally and it's easier to pull it out of the micro than it is to put another crystal in. But with only 8 pins, you don't want that. So we want to disable that. Startup times, because we are not going to use the reset line, we're going to set the reset active internally and use that pin as an IO pin, because again on the ATtiny85 you only have 8 pins. You don't want to waste one for a reset. Same reason you don't want to waste one for a clock. What the startup time does, it defines how long the clock is going to run before the micro comes out of reset on power up. So the idea is, if your clock is solid, your power is good, you can come out of reset faster. So you've got slight control over how long you're going to hold in reset once power comes up. And then here we have the clock source settings, and that just defines what the clock source is and what it can do. So if we go and look at the clock source, there is a selection of what we can do. So all zeros is an external clock, so you lose a pin because you obviously got to bring the clock in. Don't do that. 01 is the high frequency phase lock loop clock, and that allows you to take the internally 8 megs RC oscillator up to, I think it's 64 megahertz. So you can get quite a nice high speed clock out of it. Problem is, on the ATtiny85 you've only got 8-bit timer counters, and so they're a bit hard for getting timers at when you're clocking it flat out. Now 10 and 11 are the calibrated RC internal oscillator, which runs at 8 megs. Right, it runs at 8 megs for 10. If you run it on 11, well actually it's 3 in binary, but you know what I mean. Then this is a compatibility mode, and I'll put a comment up maybe that says what the clock frequency is here, because at the moment I can't remember. But I'll pause, hang on a sec, I'll go and have a look. Right, so we've been through them. Calibrated internal clock, also oscillator. 010 gives us an 8 megahertz clock. 0011, the calibrated internal oscillator, gives us a 6.4 megahertz clock, and that is to make it compatible with an older ATtiny device. The grayed out ones are either not used or you need to reference them somewhere else. And then, as you can see, if the 4th bit in the clock select is a 1, then we are looking at a crystal oscillator on the outside world going in on 2 pins, and the numbers change the frequency that it expects the crystal oscillate at, and so therefore I expect it changes the drive. 0100, internal 128 kilohertz oscillator, and then there's a low frequency one. We have here the various startup modes. Now there is 2 bits, so 4 combinations, and so it basically boils down to you have 4 options of which you can use. So like if you have an external clock, when you're powering up, the reset will be released 6 clock cycles after the clock has started, and then you get an additional delay on top of that of 14 clock cycles here, 14 clock cycles plus 4 milliseconds, 14 clock cycles plus 64 milliseconds, and you'll see the 4 and 64 things like that crop up a lot. Now if you're into the high frequency phase lock loop, then it starts getting a bit silly. 4 clock cycles plus 1024 clock cycles plus 4 milliseconds, or you can have 14 clock cycles plus 16,384 clock cycles plus 4 milliseconds, and it goes on. You can have 14 plus 1,064 milliseconds, or a 14 plus 16,064 milliseconds. But then you get from reset, you get an additional 4 milliseconds. And then for the internal one, obviously it's a bit more stable, so you can come up within 20 clock cycles, either straight after 20 clock cycles, or 20 plus 14, or 20 plus 64. This is how I read it anyway. And then again, from the low frequency oscillator, they're expecting the low frequency oscillator to be a bit more unstable, and so they're allowing a lot more clock cycles for the clock to establish. And the idea of this is, rather than saying, we'll hold the reset on power up for so many milliseconds or so many microseconds, normally you would hold it down long enough for your clock to get going and be stable, and that's why they do it this way. They're kind of guaranteeing that after 1,000 clock cycles, the clock should be running nice and stable, and therefore it's safe to release the reset. And again, for the crystal oscillator, there are various different number of clock cycles before reset gets released, and then there are the additional 14 plus various times as well. The majority of this though happens so quickly that the reset appears to come up pretty quick, and so I tend to be using at the moment the default, which is the calibrated 8 megs clock, and I turn off the divide by 8, so I have an 8 meg clock, and 6 clocks plus 14 clocks plus 64 milliseconds. 8 megs, a clock cycle is irrelevant, they're so fast. The 64 milliseconds is the most dominant bit. The clocks are so fast, it's only that milliseconds that dwarfs those. So that's my understanding of that, and we should really put that into practice. Well, this is that put into practice. And there's the setup. ATtiny MPLAB PICkit4, and over there the oscilloscope. So what I do, it's not much really to see, so I'll leave it back there. And what we'll do, bear with me, as we pull up the MPLAB, and here we can have a look at these settings. And so basically I can program in the various settings. This is the 8 megs clock with 16 clock cycles, 14 clock cycles, and no millisecond delay, and that's just a simple matter of programming it in. Oh, got no voltage. Put it back on. Do it again. There it goes. And on the screen I'll just pop up the trace from the scope. And so then it's a simple matter, if you want to do another one, we can do that one. Hit the button. Down it goes. I'll pop up a screen showing you what that one did, and then the final one for the 8 meg internal clock. That's that one. There's not much excitement to see. And again, I'll pop up the screen. And so if you should whet your appetite for the MPLAB PICkit4 and the Arduino, then let me know. Click on the subscribe, ring the bell. The next video I think we'll be doing the debug wire, so we'll have less connections to the board. If you look at it currently, I'll just move this out of the way. Currently you can see we have the full headers. If we go to the debug wire, we can reduce that connection down to 3: power, ground, data. And so that will be on the next video. So bye for now.